Hello dear students, my name is Yeshua and I'm a chemistry instructor at Kelebawiyan International Academy. How have you been doing? Today we're going to revise the second unit of grade 11 chemistry textbook. Well, this unit is very voluminous, so we're going to divide it into two halves and we'll only focus on the first half of this unit only for today. So stay tuned. Atomic structure and the periodic table. Dalton's atomic theory. Dalton was the first person who forwarded his atomic theory, and always when the issue of atomic theory is raised, well, John Dalton's atomic theory always comes first. So John Dalton was an English chemist, forwarded his atomic theory after he meticulously studied the works of other scientists who studied different things before him. So after he composed his atomic theory, then normally he released his atomic theory, and normally his atomic theory contains the following 5 statements. The first statement of Dalton's atomic theory says elements are composed of extremely small particles called atoms that are indivisible and indestructible. 2. All atoms of a given element are identical, meaning they have the same size, mass, and chemical properties. 3. Atoms of one element are different from atoms of all other elements. 4. Compounds are composed of atoms of more than one element. The relative number of atoms of each element in a given compound is always the same. And number 5, chemical reactions only involve the rearrangement of atoms. Atoms are not created or destroyed during chemical reactions. Well, these are some of the 5 statements of Dalton's atomic theory. Immediately after Dalton's atomic theory, well, we move on to another atomic theory, which is 100% accepted in modern day chemistry, that is modern atomic theory. So the modern atomic theory does also contain important statements. And what are some of its important statements? Well, let's have a look at some of the statements that are found in modern atomic theory. So the modern atomic theory says or states that atoms of one element are the same, while atoms of different elements are different. And the second statement of modern atomic theory says atoms of the same element, meaning atoms with the same number of protons with different numbers of neutrons, are called isotopes. And the other statement of modern atomic theory states most naturally occurring elements exist as isotopes. As we can explicitly see here, the statements that are found in modern atomic theory are completely accepted these days, or are completely accepted in modern day chemistry. Well, some of the statements that Dalton had forwarded do contradict with some of the statements that are mentioned or that are included in modern atomic theory. For instance, John Dalton did not have any idea about the presence of isotopes, but in modern day chemistry, well, it's obvious, or it is well known, that isotopes exist. Well, what are isotopes? Well, we'll be coming to what isotopes are in our upcoming discussions. The other point is about how the modern theory explains the mass laws. And as we all know, chemical compounds are formed when atoms combine in whole number ratios, and this description is supported by one of the laws in chemistry, which is called the law of multiple proportions. So the law of multiple proportions says that chemical compounds are formed when atoms combine in whole number ratios. And a given compound always has the same relative number and types of atoms. Law is known as the law of constant composition. And now let's move on to the discovery of electrons. Well, normally electrons are one of the subatomic particles, and it is known that atoms are the smallest particles of substances, and an atom is further divided. Well, normally that atom will give rise to subatomic particles. So normally when we always say subatomic particles are of three types, and these are electrons, protons, and neutrons. And electrons are, those subatomic particles that reside on the shells elements, or on the shells of atoms, of course. So we know that an atom has two parts, and one of the parts that an atom has is called an energy level. So always on an energy level, we get subatomic particles called electrons. And the other component of an atom is known as the nucleus, which is the central part of an atom. And in the central part of an atom, the other two subatomic particles, namely protons and neutrons, reside. Well, this is one important fact regarding these subatomic particles. And of course, subatomic particles do also have, other characteristics. Like, for example, subatomic particles have charges. For instance, in the case of electrons, normally electrons are negatively charged, whereas protons are positively charged, and neutrons are zero charged, meaning they don't have a charge at all. So specifically now when we talk about the discovery of electrons, well, discovery of electrons, one British physicist and Nobel laureate called Sir Joseph John Thomson played a very crucial role. So Sir Joseph John Thomson, which is in short called J.J. Thomson, 1856 up to 1940, was a British physicist and Nobel laureate. Sir Joseph Thomson was born near Manchester, England, and educated at Owens College, now part of Victoria University of Manchester, and Trinity College, University of Cambridge. At Cambridge, he taught mathematics and physics, served as Cavendish Professor of Experimental Physics, and was Master of Trinity College. He was also President of the Royal Society from 1915 to 19 and Professor of Natural Science. Well, here when we talk about the discovery of electrons, well, we should also say a few words about cathode rays. So this English physicist called Joseph John Thomson in 1897 studied the behavior of cathode rays in electric and magnetic fields. Thomson established clearly the rays consist of negatively charged particles. Moreover, his experiments showed that the particles were identical regardless of the materials from which the electrodes were made or the type of gas in the tube. Thomson concluded that these negatively charged particles were constituents of every kind of atom. We now call these particles electrons, a term that had been coined by the Irish physicist George Stoney in 1891 to describe the smallest unit of electric charge. Cathode rays are beams of electrons. Then in 1909, Robert A. Millikan, an American physicist, determined the charge on the electron by observing the behavior of electrically charged oil drops in an electric field. Based on careful experiments, Millikan established the charge on an electron as E is equal to minus 1.602 times 10 raised minus 19 coulombs. Alright, dear students, thus far we've been discussing about three things, namely Dalton's atomic theory, modern atomic theory, and the discovery of electrons. Now it's time for us to move on to the other very important point, which is called radioactivity. Stay tuned. So what is meant by radioactivity? Well, radioactivity is the spontaneous emission of radiation from the unstable nuclei of certain isotopes. Isotopes that are radioactive are called radioactive isotopes or radioisotopes. Well, there are different isotopes or radioisotopes, and one of the well-known radioisotopes is called uranium. And of course, uranium, as we all know, is one of the important elements which is widely used in nuclear reactors. So our next discussion will be about the discovery of the nucleus. So a short while ago, said a few points about the nucleus. Remember, the nucleus is one of the components or is one of the parts of any atom, because any atom is made of two important parts, and one of the parts is called the shell or the shells, or sometimes shells are also referred to as energy levels, and the second and the most important part is called the nucleus. So the nucleus is the central part of an atom, and in this central part of an atom, as has already been said, two important subatomic particles reside, and normally these two subatomic particles that reside there in the nucleus are protons and neutrons. Because of the presence of protons, the nucleus is charged. And what sort of charge does the nucleus have? Well, the nucleus is a positively charged component of an atom. Well, what's the reason why the nucleus is positively charged? Well, the reason why the nucleus is positively charged is because of the presence of protons. Now, the radioactive elements such as radium, uranium, and polonium undergo chains, causing them to emit alpha particles, or simply helium nuclei. The English physicist Ernest Rutherford in 1911 utilized these alpha particles to determine the structure of atoms. Thomson decided to use alpha particles to probe the structure of atoms. Well, what are atomic masses and isotopes? So a short while ago, particularly when I explained about modern atomic theory and Dalton's atomic theory, mentioned the term isotope or isotopes. Let me say a few words about what isotopes are and the sort of characteristics they have. So atoms of the same element having different mass numbers are called isotopes of that element. For most elements, nuclei of atoms of the same element can contain different number of neutrons. For example, there are distinctly different kinds of hydrogen, commonly called hydrogen protium, deuterium, and tritium. So there are different elements that have different isotopes. So when we specifically talk about the isotopes of hydrogen, well, normally hydrogen does have three different isotopes, and these three different isotopes are protium, deuterium, and tritium. So these elements have their own isotopes. For instance, hydrogen, boron, oxygen, magnesium, and chlorine. So when we simply consider these elements, normally these elements are elements that have isotopes. Remember what I've already said about isotopes. Normally these are atoms of the same element having different mass numbers are called isotopes. After the issue isotopes is mentioned, then immediately another term called relative atomic mass comes, because the issue of isotopes and the issue of relative atomic masses is highly interrelated, meaning we cannot separate relative atomic mass isotopes, or we separate relative atomic masses from isotopes. What are relative atomic masses? So the atomic mass is a relative mass of an atom determined by comparing its mass with the mass of carbon-12, which is used as a standard and arbitrarily assigned to have a mass 12 AMU. So this is what is meant by relative atomic mass. Still, we do have another very important term, which is called average atomic mass, or average atomic masses of elements. So what can we say about this term, or what can we say about the average atomic masses of elements? So the average atomic mass, also known as relative atomic mass of an element, is the average of the masses of its naturally occurring isotopes. Its unit is AMU, or it's an acronym that stands for atomic mass unit. So atomic mass is calculated by multiplying the isotopic mass of each isotope by its fractional or percent abundance and adding all these together. So whenever we are asked to calculate the atomic masses of certain elements, then what should we do? Well, we should do this. Well, we can simply multiply the isotopic mass of each isotope by its fractional or percent abundance and adding all these together. then finally a number is going to be gotten, and of course that number which is going to be gotten is the atomic mass of that element. But let's move on to another very important term, which is called electromagnetic radiation. So what is meant by electromagnetic radiation? Now, electromagnetic radiation can simply be defined as is the emission and transmission of energy in the form of electromagnetic waves. So it is the emission and transmission of energy in the form of electromagnetic waves. So the wave properties of electromagnetic radiation are described by two interdependent variables, namely frequency and wavelength. That visible light occupies a small portion of the continuum of radiant energy, which is known as the electromagnetic spectrum. Now the atomic models. So the first atomic model that we're going to see here is Bohr's model, or the Bohr model. So in 1913, Niels Bohr, applying Planck's ideas about quantization of radiant energy, suggested that the electrons in an atom revolve around the nucleus of an atom only in certain discrete orbits, with no other orbits being possible. This means that an electron could have only certain energies, meaning could occupy only certain energy levels, and that it must absorb or emit energy in discrete amounts as it moves from one allowed energy level or orbit to another. Bohr's atomic model of the atom was also based on the laws of planetary motion. He imagined the electrons to be orbiting around the nucleus as planets revolve around the sun. The Bohr model still serves as a model in studying the atom. These are the shortcomings of Bohr's model. Properly described how electrons revolve around a nucleus, and explained relationship between a nucleus and energy levels. Still, particularly his model still has some shortcomings. So what are some of the shortcomings of Bohr's model? Well, one, it could not explain the observed spectra of more complex species, and two, it gave no basis for correlating or understanding chemical bonding in terms of electronic properties. So as far as Bohr's atomic model is concerned, well, these are some of the important points that you have to remember. Let's also bear in mind that Bohr's model does also have some shortcomings. The next model is called the quantum mechanical model. So the quantum mechanical picture of the atom treats electrons as waves more effectively than as small compact particles. So here an atom has two important parts, and these are the nucleus and the energy levels. So the energy levels are also known as shells and are designated by the letters K, L, M, N till Q. Then the K shell is the first energy level, the L shell is the second energy level, and what have you. Well, thus far we've seen two important things, or two important models. Well, one of the models is called quantum mechanical model, and the other model is called the Bohr's model. Now let's see some other important things. That is the discovery of neutrons. The 1920s and early 1930s, alpha particles were used as projectiles to bombard a variety of materials. Bombardment of beryllium atoms produced a strange, highly penetrating form of radiation. In 1932, James Chadwick showed that this radiation was best explained as a beam of neutral particles. These particles are called neutrons, were found to have about the same mass of protons but no electric charge. This discovery finally provided an explanation for the mysterious excess mass. A helium atom has 2 protons and 2 neutrons. Because protons and neutrons have roughly the same mass and electrons have almost no mass, the helium atom should have about 4 times the mass of hydrogen atom. So the mass of a neutron, which is Mn, mass of neutron, equals 1.67493 times 10 raised to minus 27 kilogram, is about 1,840 times the mass of electron. So thus far we've seen the following important points regarding our today's revision. Well, what are those points that we've seen thus far? Well, thus far we've seen the following things. One, about Dalton's atomic theory, all the statements that are found in it. And next, modern atomic theory and all the statements that are found in it. Then we also saw about how the modern theory explains the mass laws, and here we saw two important laws that govern different theories. One, the law of multiple proportions, and the second is the law of conservation of mass. The other point was about the discovery of electrons, and we also said a few points about what subatomic particles are, and we said that subatomic particles are three in number, namely electrons, protons, and neutrons, and we also saw their charts. Then we saw the importance of cathode ray, or cathode rays, particularly during the discovery of electrons. Then we also saw the works of Robert M. Millikan, the American physicist, particularly when he determined the charge of electrons. What radioactivity is, well, the discovery of the nucleus, the discovery of neutrons. We also compared, we also saw the different elements that have different isotopes. We said a few words about electromagnetic radiation. Then we also saw the theories, the two important theories that are known in chemistry, namely the quantum theory and photon Bohr model of hydrogen atom, and the limitations or the shortcomings of the Bohr's theory. So that this unit is a very voluminous unit, so easily cover everything that are found here in this unit today. Well, the rest of the things will be thoroughly covered in our next classes. But before we wind up this class, or before we wind up our today's discussion, well, let's have a look at some questions. So let me pose some questions and let you attempt these questions. So let me begin with the first question, which says, what are isotopes? So, well, in our discussion, a few words about isotopes. What are isotopes? Normally, you can answer this question by saying isotopes are atoms with the same number of protons but a different number of neutrons. Well, the second question, a multiple choice one, and it says hydrogen has three isotopes and relative atomic mass of 1.0079. Which isotope is the most abundant? A, hydrogen with atomic mass of 1, B, hydrogen with atomic mass of 2, or C, hydrogen with atomic mass of 3. So you can easily apply explanation that has already been given to calculate the relative atomic mass, or the relative atomic masses of certain isotopes. Well, we discussed about that a while ago. So anyway, the answer to this question is A, meaning hydrogen with atomic mass of 1 is the most abundant isotope of hydrogen. And besides, as you remember, we mentioned certain elements with their isotopes, and one of the elements we mentioned was hydrogen. So normally hydrogen has three isotopes. Isotope, which is abundant, or which is most abundant, is hydrogen with atomic mass of 1. So if you answer this question by saying A, then you're correct. The third question is also a multiple choice one, or in a nuclear reactor, electricity is produced from what element? A, from plutonium, B, from uranium-235, C, from radon-220, D, from lead-232. Well, the answer is B, uranium-232. Last question. What are the two wrong statements of Dalton's atomic theory? Well, one, the indivisibility of an atom was proved wrong, meaning was proved to be wrong because Dalton did not know whether atoms could further be divided into other teeny tiny or infinitesimal things called subatomic particles. So here, this can be regarded as one of the shortcomings of Dalton's atomic theory. And the second is, or the second shortcoming of Dalton's atomic theory is that the atoms of the same element are similar in all respects. So this is also the other wrong statement of Dalton's atomic theory. Alright, dear students, thus far we've been revising some of the important points of this unit, and I'm sure you really enjoyed the lesson. And next time I'll be coming with the remaining parts of this unit, meaning Unit 2. Till then, have a blessed week. Bye-bye.